Today I will present the results of an econometric analysis examining how budget per capita affects revenue per capita. I will explain the model, estimation method, assumptions, interpretation of results, and policy implications for Universal Motors. The central question of this study is what happens if Universal Motors raises or lowers its budget per capita? Our hypothesis is that a higher budget per capita will increase revenue per capita. The economic reasoning behind this prediction is straightforward. When more financial resources are allocated per capita, the organization can improve operations, invest in infrastructure, enhance service quality, and potentially expand marketing efforts. These improvements should lead to higher revenue generation. Before estimating the model, I examined the data descriptively. There was a strong association between the budget and revenue with no extreme outliers during the model. The dataset consists of 388 cross-sectional observations. The dependent variable is revenue per capita, and the key independent variable is budget per capita. To isolate the effect of budget, I included control variables capturing demographic and economic characteristics such as population, income, education, age, unemployment, rainfall, and advertising price index. The estimated model is a linear regression where revenue is expressed as a function of budget and these control variables, plus an error term representing unobserved factors. The model is specified in linear form for several reasons. First, the linear specification allows for direct interpretation of marginal effects. The coefficient on budget directly tells us how much revenue changes when budget increases by 1 unit. Second, the scatter plot suggests an approximately linear relationship between budget and revenue. Third, linear models are standard in applied economic policy analysis and provide a straightforward interpretation for decision making. Control variables were included to reduce omitted variable bias and ensure that estimated budget effect is not confounded by demographic or economic differences across regions. Before finalizing the model, I tested whether the relationship between budget and revenue might be nonlinear, such as showing diminishing returns. I compared linear, quadratic, and log specifications, and the results were very similar and no strong curvature appeared in the data. In this analysis, I used ordinary least squares or OLS as the estimation technique. OLS estimates the regression coefficients by minimizing the sum of squared residuals, that is the squared differences between the observed values of revenue per capita and the values predicted by the model. By minimizing these squared errors, OLS finds the best fitting linear relationship between the dependent variable and the explanatory variables. Under the classical linear regression assumptions, such as linearity, exogeneity, and no perfect multicollinearity, OLS is the best linear unbiased estimator, meaning it provides the most efficient linear estimates among all unbiased estimators. However, one important concern in cross-sectional data is heteroscedasticity, which occurs when the variance of the error term is not constant across observation. If heteroscedasticity is present, the OLS coefficient estimates remain unbiased, but the standard errors may be incorrect, leading to unreliable hypothesis testing. To address this, I used robust standard errors, specifically the HC1 correction. Robust standard errors adjust for potential heteroscedasticity and ensure that the potential p-values and confidence intervals remain valid even if the error variance is not constant. This strengthens the reliability of our statistical inference. The analysis was conducted using Python in a Google Colab environment. I used the stats models package to estimate the OLS regression. Fixed effects were implemented using categorical indicators for region and months. Clustered standard errors were computed at the regional level. The workflow included data cleaning, variable preparation, regression estimation, and graphical analysis. Now I turn to the regression results. The estimated coefficient on budget per capita is 0.384. This means that, holding other variables constant, a 1 unit increase in budget per capita increases revenue per capita by 0.384 units. The p-value associated with this coefficient is 0.012, which is below the conventional 5% significance level. This indicates that the effect is statistically significant. The 95% confidence interval ranges from 0.086 to 0.683. Since 0 is not contained within this interval, we reject the null hypothesis that the true effect is 0. Importantly, budget is the only variable that is statistically significant in the model. Let me clarify what these statistical measures mean. The point estimate of 0.384 is our best estimate of the true population effect. The p-value tells us the probability of observing such a coefficient if the true effect were actually 0. Since the p-value is 0.012, the evidence strongly suggests that budget has a real effect on revenue. The 95% confidence interval provides a range of plausible values for the true effect. Because 0 is not inside the interval, the effect is statistically significant at the 5% level. Together, these measures confirm that the relationship between budget and revenue is positive and statistically reliable. Next, I examine the regression diagnostics. The residual histogram shows a roughly symmetric distribution centered around 0, suggesting that the error term does not exhibit severe skewness. The QQ plot shows that most points lie close to the 45-degree line, indicating that the normality assumption is reasonably satisfied. Additionally, robust standard errors were used to account for potential heteroscedasticity, strengthening the reliability of inference. Overall, the diagnostics do not indicate major violations of classical regression assumptions. The variance inflation factor results indicate that some demographic variables exhibit high multicollinearity. In particular, average age and education show high VIF values, suggesting a strong correlation among explanatory variables. Multicollinearity inflates standard errors and may explain why many control variables are statistically insignificant. However, the VIF for budget per capita is low, meaning that the estimated effect of budget is not distorted by multicollinearity. Although the model explains a modest portion of total variation in revenue, it provides statistically significant evidence that increasing budget per capita increases revenue per capita. From a policy perspective, this suggests that budget allocation decisions have measurable revenue consequences, though additional variables may improve predictive power. Thank you very much for your attention.